Any other questions? Okay, let's go through a review of this for a few minutes, and then we'll do the quiz. So, can anybody remember what the symbol is for the mean of the sampling distribution? Anybody remember the symbol for the mean of the sampling distribution? What? What? Almost. Not quite. Anybody remember it? But they have two symbols. They have the mean of a population, and they have the mean of sampling distribution. Anybody remember what those two are? What is it? Right. Can you write it on the board? Thank you. Write both of them so we can see that they're not the same symbols. Right. So mu versus mu sub x bar. Are those the same things? No. Right? They're not the same. What's the difference? Do you remember? The second one is kind of complicated. Right? What is it? It's if you, let me say it this way. If you repeatedly sample from a population, so you take a sample, you calculate x bar for that sample. Then you take another sample, x bar of that sample. Then you take another sample, x bar of that sample. Every time, when I say sample, I mean you take a sample from the population and you throw it back in after you're finished. So you can keep doing it over and over again. Okay? So you keep doing this, sampling x bar, sampling x bar, sampling x bar, sampling x bar. And then what? You look at the pattern of the x bars that you get. What do you get? So obviously you're going to get different things each time because each sample is different. But was there anything, and the other thing is that you don't have to get mu each time, right? When you take a sample, you're not necessarily, the mean of that sample is not necessarily going to be the mean of the population, right? There's no reason for it to be, right? Okay? So we don't expect to get, all these x bars that we get to be equal to the mu. That would be very unreasonable, right? It would be very demanding of us, right? We don't believe that. So, is there anything, though, that we were able to say about this? About the use of x bar? Well, let's see. What? What were we able to say about mu sub x bar? It's equal to mu. Is that believable or not believable? Here's mu. This is the population of that's the mean of the real population. Okay? That's the mean of the real population. Now I have the whole population here. Mu is there. I take a sample. Am I going to get, if I calculate x bar for this, is that going to be equal to mu? Not necessarily, right? So it might be here. And then I do it again. I get another mu. I get another x bar. I get that one. Then I do it again. I get another x bar. I get that one. But what about this? That means if I keep doing this, what's the mean of these x bars that I get? So sometimes they're going to be above mu, sometimes they're going to be below mu, but we can say on average, that's what this means, on average, what can we say about the x bars? They're going to be equal to mu, right, on average. So that's what this statement says. Okay? Okay? Now there was one more question, and that was about this. So first of all, what does that mean? What does that mean? That's saying how much spread are we going to have in these x bars? Right? So yeah, sometimes we'll get an x bar here, sometimes here. There's going to be some spread in these x bars. The question is, how much spread is there going to be? And the question might be, is this like that? Or is it like that? Or is it equal? Okay, now what does this mean? This is the spread of the x bars compared to the spread of the original population. So what did we say about that last time? The spread of the population, remember, if this is people's heights. We talked about that. Or let's talk about fat people. Everybody likes to talk about fat people. Let's talk about fat people. So it's possible that we might find somebody at APU who has a weight equal to 120 kilograms. Not too likely, but it's possible, right? So, but what about the chance of finding, suppose we take samples of size 100. What do you think is the chance that we get, and the average of 100 people is equal to, weight is 120? That's very, very unlikely, right? Right? If you take 100 people from APU, what are the chances that the average of those 100 people, their weight is going to be 120, right? That's not too likely, right? So what are we saying? That it's possible to get big, that the spread of x bar, the spread of x is bigger than the spread of x bar, right? Because you're not likely to get an x bar which is way out here at 120. It is possible that you get one person, but not 100 people. That's the average is equal to 120. Okay, so which of these is true? This one or this one? I or II? Which of those is true?
I.
Right. The spread for x bar is going to be less than the spread for x. And then, not only that, but we ended last time with even more precision about this relationship. So not only can we say that it's less than, but we can actually give the formula for the relationship between the two. What was it? This is that. So that shows that this one is smaller than this one, because this one is this one divided by something. So it is smaller, and this tells you exactly how much smaller it is. And it's a function of n. N being what again? The sample size. So what does that mean? The bigger the sample size, the less spread we expect to get. Right? We don't expect to get as much bouncing around when we take a big sample, right? Because we get a lot of averaging. Right? So we get less. And so that's the relationship. Okay? So that's what we discovered last time. That's where we left off last time. So let's do the quiz now. So the quiz should be there. Okay, so we just saw this, right? Now, they said this formula is used when n over n is less than 5%. So what does that mean? Let's suppose that our whole population is all APU students. Okay, suppose we have all APU students in our population, and we take a sample of size 100. Is that true in this case? Is n over n less than or equal to 0.05? So what is small n? 100 over large n is? What is that? Oops, sorry. 1 over 60, right? Which is what? Well, less than 2%, right? Less than 2%. So it's satisfied here, right? In that case. So if n over n is less than 0.05, we can do that. How about if I start taking a bigger sample size? How about if I did 2,000? I'm sorry, 200. Now it's going to be what? 2 over 60, what's that? 2 over 60 is what? 0.0333, okay. That still works, okay. How about if I did 500, a sample of 500? Now what? So it's 500 over 6,000. It's 5 over 60. That's bigger. Right? That's bigger than 0.05. Right? So that would be what? That means that the bigger our sample size is, we have to be more careful about using this formula, which tells us what? The spread of sigma x bar. Okay, this formula doesn't really hold when sigma x bar gets, I'm sorry, when n gets too large. Okay, is that clear? When little n gets too large in relationship to big N. That make sense? Okay, next though, if that is not true, if it's not less than 0.5, if the condition is not satisfied, 0.05, we use the following formula. So now we use this, the first part is the same here, but we add in this part here, and that's called the correction factor. Okay, that's when n is bigger, when n is relatively large. When little n is relatively large. So what happens when little n gets larger here? What happens to this? What's this part? What happens here when little n gets large? That's n minus little n. That becomes smaller and smaller, right? The difference between capital N and little n becomes smaller and smaller. So this part stays the same. So we're, what are we doing? What's happening to this as little n gets bigger? What's happening to this as little n gets bigger? Okay, before you answer that, what do you think should happen as little n gets bigger? Well, here we can see already. As little n gets bigger, what happens? This gets smaller. We get less variation, right? Now, does this go against that or reinforce that? So as little n gets bigger, this becomes smaller, so it even reinforces it more, right? Okay, is that clear? Okay. So, and what is this factor called? The finite population correction factor. So why do they say it's the finite population correction factor? Because if the population was infinitely large, then this would always be true, right? If the population was infinitely large, then this would always be true, or not even infinitely large. But if n was really, really big, capital N was really, really big, then this is always going to be true, right? So when this only becomes a factor when capital N, the population size, is not so big anymore. Okay, does that make sense to everyone? Okay, so we saw this already. I said this just a few minutes ago, right? That this one is smaller than this one. The standard deviation of the sampling distribution decreases as the sample size increases. We already said that also. Okay, now let's try an example. Okay, so by the way, I think we'll have some group work today. So you guys will have to explain to each other this stuff, and then we'll answer it in a group, or you'll answer it for your group, I should say. Okay, so let's try this one. The mean wage for all 5,000 employees, that's like all 6,000 APU students, who work at a large company is $27.50 per hour, I guess. And the standard deviation is $3.70. Let X bar be the mean wage per hour for a random sample of certain employees selected from this company. Find the mean and standard deviation of X bar for a sample of size 30, 75, and 200. So go ahead and try and do the first one yourself. So do A yourself. So the question is to find the mean and standard deviation of X bar. So first of all, before you do that, what about the correction factor? Do we need it or not? Why do we not need it? Because when we take a sample of 30 from 5,000, that's what, 3 over 500, that's definitely less than 5%, right? Okay, so we don't need the correction factor, at least not for this one. So go ahead and do it. I think I wrote it here. Yeah, it's written there, so you can see it up there. So you want to get two things. You want to find the mean for X bar and the standard deviation for X bar. So these are theoretical. You're not actually you're not finding the mean of something in particular, like of data. So mu sub X bar is 27.5, and sigma sub X bar is 3.70 divided by the square root of 30. Okay, good. So here, mu sub X bar is equal to mu, which is 27.5, and sigma sub X bar is equal to sigma divided by the square root of n. So it's this. So the standard deviation is only 0.6 or 0.67, or about 67 cents, right? For a sample of 30 people. Okay? Okay, how about for B? Then it was, what was the size here? 75. So this is still the same, and this one is divided by the square root of 75. So it's smaller. It's not 67 cents anymore, it's 42 cents. That means the the spread, in other words, we're going to calculate x bar, we're going to calculate x bar, we're going to calculate x bar, we're going to do it many times. What kind of spread is there in this x bars that we get? And now it's only going to be like about 43 cents. And how about here? Now it's only going to be about 26 cents. Okay? Okay, now, last question, or last thing here about the sampling distribution. So we've said two things about the sampling distribution. What are they? We talked about the mean of the sampling distribution, and we talked about the spread, or standard deviation of this sampling distribution. Last thing we're going to talk about is what? The shape of the sampling distribution. So what does that mean? Again, it's the same scenario. We have a population. We calculate an x bar. We calculate another 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 x bar, and so on. And if we kept doing this, we're going to get, we can ask, what's the distribution? How much of the time are we going to get an x bar out here, like really far away, and how much of the time are we going to get x bars really close? So what's the distribution of the x bars? What's the probability distribution? How likely is it that we'll get something way over here, and how likely is it something we're going to get something really close, and so on? So that would be pretty fantastic if we could give an answer to that. Because we're talking about for any population, right? It's kind of, so you have to, first of all, the kind of answer we're going to give is going to have to be, in some sense, general. So at least it's going to have to depend on the original population's mu and the original population's standard deviation, right? Otherwise, just can't just give it any old answer, right? But in terms of the shape, well, let me ask you something, maybe this one. As n increases, let's suppose we had the original population look like this. Look like that. So this was, let's say, these are people's weights. So let's say this is 60, and there were a lot of people that weighed like 90, and a lot of people that weighed like 40. Okay? And so suppose that was we had some weird population of people that had this probability distribution for their weights. Okay? Now, if I just take one person at random from that population, and I keep doing that over and over again, what's the distribution, and I'm sorry, and I calculate x bar. In other words, I take a sample of size 1, and I calculate x bar. Of course, x bar is just the single value, right? If I take one person, and I say, okay, this person weighed 68, and then I say, what's the average of that sample? Of course, it's 68, because there's only one person in there, right? So what's the what I'm going to get, what kinds of x bars? I'm going to get exactly the same as the original population was. It's going to look exactly the same. Okay, but if I take 10 people and from this weird population, and I take a sample, and I say, what's their average? And then I take another sample, and I say, what's their average? And then I take another sample, and I say, what's their average? Right? Now what? Now the spread is going to be more narrow. And what could we guess? I'm not saying you really could guess, but if you want to make a guess, that's fine. What could we guess about the shape of this distribution of these x bars that we're calculating? So will it be this again? But we already said it's going to be more narrow, so it really can't be this, right? We already said it's going to be more narrow. So what might it look like? Well, that's the question we're trying to answer here. Okay? Now that's a weird question, you have to admit. I mean, it's weird to imagine that there's an answer to that question. You know, given any weird shaped population, can we say, when we calculate x bars, can we say what the shape of the distribution of the x bars is? It sounds like no. How could we answer such a question? Right? How could we answer it in general for any population? Right? Do you understand? But it turns out, kind of miraculously, that there is an answer. Okay? So let's see what they say. The shape of the sampling distribution of x bar, the population from which samples are drawn. Okay, now here they're saying, suppose that the original population was normal shaped. So the original one didn't look like that, it looked like that. Right? Okay. Well, in that case, maybe we could make a guess, because we're just saying, specifically the original population was normal, so it doesn't seem so unlikely that we could guess about the shape. But if it's not normal, that's case 2, right? The population from which samples are drawn does not have a normal distribution. In that case, it seems unlikely we could give any answer. Right? Okay, so let's see. So they break it up into those 2 cases. Well, the first case is kind of not interesting, because it seems kind of, well, sure, we're going to be able to answer that. Okay, so anyway, let's still answer that question. Sampling from a normally distributed population. If the population from which the samples are drawn is itself normally distributed with mean, mu, and standard deviation sigma, so we just say, suppose it has some mean, which we'll call mu, and it of course has some standard deviation, we'll call it sigma, then the sampling distribution of the sample mean, that is the sampling distribution of this x bar, will also be normally distributed. Okay, but that's not so super surprising, right? But, and we already know what the mean of it will be. We already did this part here, and we already know what the standard deviation of it will be. So we now know that if we start with a normal population, and we sample from that population, and we calculate the x bars, we know what the distribution of the x bars will be. It's going to have a mu equal to the mu of the original population. It's going to have a standard deviation according to this formula, and the shape is going to be normal. Okay, so here's the picture. This is the original population. We said suppose that it's normally distributed. That's case 1. We're examining case 1 where it's supposedly normally distributed. Now we take a sample of size 5. Then we take a sample of size 16, then 30, then 100. What happens? The sampling distributions for all of them are normal. So what's the difference? What's the difference between this one and this one? They're both normal. The difference is what? The spread. Right? They're all centered still at the same place. The difference is what? The spread. What happens to the spread as we get bigger, as we do it for larger sample sizes? The spread becomes narrower or smaller. The spread becomes smaller, right? Which is what we said, right? That's what we said in these formulas. The spread is getting less and less and less and less. So this shows that picture, okay? But this is not that surprising, as I said, given everything we've said already. Okay, but that's the answer. Any questions about this? Now, this seems kind of very theoretical, and, maybe it's fun, kind of a little bit interesting, and but it seems like not very practical. But it turns out it's very practical. Okay, we're going to have a lot of use for this. Okay, so here's an example. So let's try this one. So you can try this one as well. So what does it say? In a recent SAT, what's SAT? That's an exam that you have to take to go to a U.S. university, undergraduate school. Shh. Who's talking? Shh. Okay. In a recent SAT, the mean score for all the students, that means the population, right? The population mean was 1020. Assume that the distribution of SAT scores of all people, that means for the population, is 120, and the standard deviation for the whole population is 153. Okay? We're going to read this so far? We're going to pick it up so far? Okay. Now, let X bar be the mean SAT score of a random sample of certain examinees. Calculate the mean and standard deviation of X bar and describe the shape of the sampling distribution when the sample size is 16. So actually, we already did this kind of question, but the only difference is what's the shape, but you should know that now that I just finished the previous slide. But okay, just do it. Okay, now let's do it. Let's see the answer. So here it is. This was original. So the mean is also centered at the same place, but the spread is this. Now, don't they draw a picture? Yeah, here. Okay? So here's the original one was here, 153 spread. But for X bar, it's what? It's much smaller, right? It's 1/4 the spread. Is that clear to everybody? It's 38 versus 153. Okay? Okay, and then we can do the other ones as well. They look like this, and they look like that. Okay? All right. So, now we have the very, what should I say? What should I call this? Now, if you learn this, you can say with great pride that you understand the central limit theorem. It sounds impressive, right? Okay, so the central limit theorem says what we've already said. It says the three things that we've already said. What are they? So it's called sampling from a population, sampling from a population that is not normally distributed. Okay, sorry, I apologize. So now's the question that's much more interesting, which is if the original population is not normally distributed, what about the distribution of X bar, the sampling distribution of X bar? So even if we have something like this, or some other weird shape, can we make any statement about the distribution of X bar? Now, you would say, well, you can't, especially when n is just equal to 1, right? Because when n is equal to 1, then we just said we're going to get exactly the original shape. So if we have different shapes than they're all to start with, then they're going to all be different. So we can't make a statement about it, about one in particular, what's going to happen. Right? All we can say is it's just the same as the original population. That doesn't nail it down at all. Okay? So if n is just equal to 1, no. We're not going to be able to say it. So it seems to depend on the size of n. So if n is bigger, maybe we can make some statement. And that's true, that's the truth. As n, that's the fact. As n gets bigger, we can say something. Okay, and what is it that we can say? Well, it's called the central limit theorem. And it says what? According to the central limit theorem, for a large sample size, that means for a large n, the sampling distribution of X bar, regardless of the shape of the original population, is basically normal. That's kind of weird, right? I mean, just seems weird. Why should that be true? For any weird starting population, if you take large samples and look at the distribution of X bar, you keep doing X bar many times, the distribution of that X bar is going to be normal, even though the original population can be any shape. You have to admit that sounds really kind of miraculous or magical, right? But it's true, okay? So that's going to need something for us. Because we know lots about, you can tell me all kinds of things about probabilities from normal distributions, right? You do a lot of homework like that. So you're going to be able to answer a lot of questions because you know about normal distributions and because X bar has a normal distribution, no matter what the original population is. Okay? So that's why I said this is very practical. You'll see in a few minutes. For a large sample size, the sampling distribution of X bar is approximately normal, irrespective of the shape of the population distribution, of the original distribution. The mean and standard deviation, we already know the formulas for those. And the sample size is usually considered to be large, that is, if n is greater than or equal to 30. So this basically holds as long as n is greater than or equal to 30. Now, if the original population is really weird shaped, then n greater than 30 won't be enough. But for most cases, yes, n greater than or equal to 30 is okay. So here is an example. So here's a kind of weird shape. It's not that weird, not as weird as I drew, but it's not normal. It's not a normal shape. What do we call this kind of shape, by the way? Skewed. We call it skewed to the right. So when you pull it to the right, that's called skewed to the right. So this one is skewed to the right. Then we look at what this distribution for X bar will be. And we do it for when our sample size is 4, when our sample size is 15, when our sample size is 30, and when our sample size is 80. And what do you see? When the sample size gets to be 30, what does it look like? It looks close to normal. And 80, it also looks close to normal. And that's an illustration of this central limit theorem. Okay? That as n increases, it's not originally normal. It doesn't even look normal for n equals 4. Or for, not really, not too bad though, for n equals 15. By n equals 30, it's really starting to look normal. And by n equals 80, it's probably looks even more normal. Okay? So now, let's see what this says. The mean rent paid by all tenants in Bethbu, the mean rent paid by all people living in Bethbu is $1,500. That's a kind of a lot for Bethbu. What? Yeah, it's really a lot. But anyway, with a standard deviation of 225. However, the population distribution of rents for all tenants in the city is skewed to the right. What does that mean, skewed to the right? It means there are some people who pay a lot. Right? Skewed to the right means it's dragged up, right? Higher. Right? So that means there are some people who pay like $5,000 for rent, right? That's what skewed to the right means, right? Okay. So it's not normally distributed. The rents are not normally distributed. Okay, guys, I'm only going to say it one more time, and then I'm going to fail you for your life. No, I'm going to ask you to leave the room. Okay, so if you keep talking, I'm going to ask you to leave the room. Keep murmuring. I'm going to ask you to leave the room. But they're not even listening, they're still talking. So you have a good question about your grade, but I don't think that's the right time to be talking about it. Okay, you can talk to me about it afterwards. Okay? So, Okay, now, let's go back to this. So, however, the population distribution of rents for all tenants in the city is skewed to the right. Calculate the mean and standard deviation of X bar and describe the shape of its sampling distribution when the sample size is this. So, well, this is kind of, we've done this like 4 times already, so there's no reason to do it again. But what's the description? Describe the shape. What's the answer going to be? Since it's 30, since it's 100, even though the original population was skewed, this is going to have a normal distribution. Okay? So we get that. And even though the original was skewed, the sampling distribution for X bar is normal with a sigma of $41. Okay? And same thing with B. Okay? All right, now let's see if we can get in it. Okay, let's read this. If we take all possible samples of the same large size, so we're taking a large sample sizes from a population and calculate the mean for each of these samples, where's this number come from? Then about 68% of the sample means will be within 1 standard deviation of the population. Where does that number come from? Do you remember any facts about normal distributions? If you go to the normal table and you look up the area, 1 standard deviation from the mean, what's the area, sorry, what's the area in here? 68%. If you look that up in the table, you'll get 68%. If you go 2 standard deviations, what's the area approximately? 98, 95, I think it's 97 something. But let's just say it's 95. Just to make it simple, we'll say it's 95%. Not exactly 95, but it's about 95% if you go 2 standard deviations. Okay? So what are they saying? What are they saying? If we take all possible samples from a population, doesn't matter what the original population looks like, and calculate the mean of these, then about 68% of the sample means will be within 1 standard deviation because it's normally distributed, even though the original population is not necessarily normal. So it's this picture, right? So can you read that up at the top, though? Looks kind of complicated, but it's a statement about X bar. It's a probability statement about X bar. So it says what? The probability that X bar is between 2 things. What 2 things? Mu minus a standard deviation. That's mu minus 1 standard deviation. We usually write that as -1 here. And mu plus 1 standard deviation, we usually write that as +1 here. The probability that X bar is in here is what it says there, right? And what's that equal to? 68% approximately, right? So the hardest part here is just reading what that top line says, right? What is that top line asking, or what it's asking? What is it asking? It's saying, what's the probability that X bar is within 1 standard deviation of the mean, right? Plus 1 standard deviation, minus 1 standard deviation. So that's what it's asking, right? And the answer to that is, because it's normally distributed, the answer to that is 68%. Okay? So really, what you learn here in this screen is how this is written, the notation that's used here. Okay, but that's important because otherwise you get confused when you read a book or you read something. Okay, let's look at an application. If we take all possible samples from a population and calculate the mean for each of these samples, then about 95% of this sample means will be within 2 standard deviations, right? I said that already. Okay? So here, if we go up 2 and down 2, what is that? The probability that something is in that range is what? 95%. And how do we write that up at the top? We say the probability that x bar is the center one, is between 2 below and 2 above is, and then the answer is 95%. Okay? Okay, if we go 3, the answer is 99%. Okay, 99%. 3 up and 3 down. Okay, now hopefully this is an example where we use it. Assume that the weights of all packages of a certain brand of cookies are normally distributed with mean of 32 ounces. How much is 32 ounces in grams? I think 1 ounce is 28 grams. 1 ounce is about 28 grams, so 32 times 28 is about 600, 700? What? 800. Okay, so imagine 800 gram package of cookies. Okay, so maybe a big bag of cookies, right? But you know that if you're manufacturing cookies and you aim that every bag is 800 grams, every bag is not going to be 800 grams, right? Some of them are going to be more, and some of them are going to be less, right? Of course. So we're saying that the mean is 800, but we don't expect that every bag is going to have the same, exact same weight, okay? In fact, the standard deviation is 0.3, which is about a third of 28. So it's 8.4. Okay, let's just make it easy and say it's 10. Okay, so sigma is about 10. Okay? Just make it easy. Okay, find the probability that the mean weight of a random sample of 20 packages of this brand of cookies will be between this number and this number. Okay, now wait a second. They didn't say that the distribution of the weights of the original population was normal. They didn't say that. How many are we taking? Just 20. So the theorem doesn't exactly hold. Oh, they did say, I'm sorry, they did say it was normal. Okay, so they did say it was normal. So, all right. So suppose that it's normally distributed and we take 20. And what are we asking? Find the probability, right? It says find the probability, right? That what? That the mean weight, so how do we express the mean weight of a sample? X bar. So find the probability that X bar is between what and what? Is between 31.8 and 31.9. Now, what were the numbers in ounces? 32 was the mean, right? No, sorry. 32 was the mean, right? And the standard deviation was 0.3. So I converted it all to grams because most of us aren't familiar with ounces. But let's do it with ounces because the numbers are already there. We don't have to convert all this perfectly, right? So anyway, this is the question. The mean is 32, so it looks like this. Here's the mean, 32. They did give us that it's normally distributed, but we want to find out that X bar, not X, is somewhere between here and here, right? Because it's less than 32. Both of these numbers are less than 32, right? So we want to go here to here, something like that. where this one is 31.8 and this one is 31.9. Okay? So the fact that they told us that the originals were normally distributed kind of takes the fun out of this problem, because we sort of already knew that the originals were normally distributed, so it's not so interesting or surprising that we can calculate this kind of answer even about x bar. So let's not go through let's just see what they say. So the mean will still be 32 even for x bar, but the standard deviation will be 0.067. And now we have to convert all of our stuff to normal, to standard normal, so that we can look it up in the table. Right? Otherwise, we don't know. Otherwise, how are we going to look this stuff up in the table? We don't have any table that has a center at 32. Our normal table's centered where? At 0, right? So we have to convert this to like this. But remember, we use sigma x bar there, because we're doing this about x bar. And that's different than before. And then we do all of the calculations. We do it for 31.8. We get this number. We do it for 31.9. We get this number. And then we want, so the probability that x bar is between here and here is equal to the probability that z is between here and here. And then you can look at those numbers up in the table and do the calculation. And you can find the answer. It turns out to be 6% or 7%. 6 or 7%. And here's a picture of that. Right? But I want to do one where it's not originally normal. Okay, good. This one. Okay, first of all, in this problem, what's the sample size? In this problem, search through the problem and find out what the sample size is. Search through the problem and find out what the sample size is. Can you see it? What's the sample size? Just don't read the whole question, just figure out the sample size. What is it? 400, okay, so we have the sample size is 400, right? Okay, now what is this about? What Sally Mae, I don't know what that is, but there's something called, anyway, I don't know what Sally Mae means, but it's a survey. About what? About credit card debt. Okay, so they're not going to tell us that it's normally distributed. Credit card debt is not necessarily normally distributed, at least they're not telling us that here. So it could have a weird shape. Okay, so that's one thing. Now, what's the average credit card debt that was owed in 2008? $3,173, right? Okay, $3,100.73. Sorry, $3,173. Okay? All right. Suppose that the probability distribution of the credit card debts for all college students in the United States is known. I think they mean unknown. I think they meant unknown there. But anyway, but it's mean because they said but, right? So you don't say it's known but, right? I think they meant is unknown but. Its mean is 3173, and the standard deviation is $750. Let X bar be the mean credit card debt of a random sample of 400 US students. Okay? What is the probability that the mean of the current credit card debts for this sample is within $70 of the population mean? Not such a. What is the probability that the mean of the current credit is lower than the population mean by $50 or more? Those questions are not so clear. A little bit complicated. How about if I ask you a different question? what's the probability that, so what was centered where? No, it wasn't, no, sorry. Not normal, we don't know this shape. Okay, but the mean was what? 3170. Is that right? 73. Okay. So suppose I ask you, we're going to take a random sample from this population. We're going to take a random sample, and let's say n equals 100. 100 people from this population, so that square root of 100 is easy to calculate. Right? And, oh, sorry, suppose, did they tell us sigma?
Yes, 750.
750, let me just change this. Let me make these numbers a little easier. Let's say it's 3,000, and sigma is, say, 200. Okay, let's just make it easy. Okay, so now we take a sample of size 100. What's the probability that this sample of 100 people will have will be less than 2980. What's the probability? So the question is, what's the probability that x bar will be less than that number? X bar will be less than, or less than or equal to 2980. So that's kind of, if you can answer that, that's kind of amazing, right? I said we have some unknown distribution of the original population, and you take a sample of size 100, right? And I do tell you this, and I do tell you this. And then I say, for the sample, what's the probability that the sample is less than this? And if you can tell me the answer to that, that's kind of amazing. How can you tell me the answer to that? The probability that your sample from an unknown population, I mean, you do know this, and you do know this, but you don't know the shape of it, and yet you're going to tell me the probability that x bar is less than 2980. That sounds kind of impressive. So can you do it? So what you need to know is the distribution of x bar. And by the distribution, I mean, where is it centered, what kind of spread does it have, and what kind of shape does it have? So can you answer those questions? Where is it centered? Where is x bar's distribution centered? At 3,000. What is its spread? No, what is its spread? What is the spread, the standard deviation? 200 divided by the square root of 100. 200 divided by 10. 20. The spread is, the standard deviation is 20. Okay, and what is its shape? Normal. Now you can do it, right? What's the probability that the random sample is less than 2980? That's one standard deviation, right? Right? 20, yeah. One standard deviation. So what is the probability that's less than one standard deviation? So this part, so we're talking about here, here. So you know that this is 68, right? You know that this is 68, right? One standard deviation in both directions. So this much is how much? 34. This is 34 in here, right? Half of 68 is 34. So this, from here to here, is 34, so how much is left over? 16, right? So, right? 16% in here. Right? 34 plus 16 is 50. Right? So So what's the probability that it's less than, right? So what's the probability that if you randomly select 100 people, what's the probability that the average of their debt is going to be less than this number? 16%. Okay? Even though we don't know anything about the shape of the original population. Okay? So let's say that. So let's not do these. Okay, that's it. So with that, maybe you can do some homework problems. Okay, now let's take a 5-minute break, and while I set up for our group stuff, I'll set that up, and then we'll have a group question.